Good evening. So let's start today's class. So as usual, I will first recall very briefly whatever we done in the previous class. Now we have reached in the course in that stage where we already learned in the previous class the most basic games or the game that will you commonly encounter if you start to read about game theory. So, first of all, in the previous class, we have learned a basic game which is known as prisoner dilemma, and this game prisoner dilemma is a uh, is very classical example of a game, and in this game we can capture the free riding tendency of any individual, or that essentially, as the name suggests, dilemma is this dilemma actually captures the situation or the dilemma faced by two prisoners who are taken to the custody, but the police doesn't have that much information to to make them convicted for a major crime before the court. Now what they will do, are taking these two prisoners into two separate rooms, and before the prisoners they presented some condition, and they presented the conditions in such a way that it means they presented in such a way that prisoners will feel that by free riding or by defecting or by confessing their crime will be more beneficial, even though if they do not confess, then they already know there are not enough evidence to make them convicted for a major crime. So that dilemma is represented by prisoner's dilemma in mathematical term. Then we have write this pair matrix. Now today we gonna see that what is the equilibrium corresponding to this prisoner dilemma. In the next game we have learned about the battle of sexes. So here we have present a game which essentially captures the situation where two individual always wants to do together something. However before however for the two different individuals, suppose there are two different things they can do together. However, one is preferred by one individual, more preferred by one individual, and for other individuals the other activity or other option is more for other option is more preferable. So that kind of situation can be captured by battle of sexes. However, here we want to make sure that in the battle of sex situation the the both individual always prefer to do something together. They don't prefer at all the situation where both of them are doing separate thing individually. So that is the least prefer. So as for an example, suppose two partner, one is male and female, are trying to go to a date, and they wants to decide where to go. The male partner prefer to go to a cricket match than a musical concert. However, the female partner prefer to go to a musical concert than cricket match, but both of them wants to go together. Now you can express this situation as a game which is known as the battle of sexes, and obviously the name uh, this game gets from the situation that I described now between the two different preferences between male and female. So in both of these battle of sexes game and the prisoner dilemma, both the conflict and cooperation part present. However, in the next we have present a strictly competitive game where the cooperation cannot be possible between two individuals. Here it basically is called strictly competitive game. And what it captures a situation where suppose suppose that we two individuals means before two individuals some condition are presented. The conditions are following that both of them has to show one face of a coin. They can show either head or tail. Now the payoff structure is such that if both of them show same face of the coin, then player 2 give player 1 one rupee, and if here both of the case player 2 give player 1 plus 1 rupees, and that means player 2's payoff is -1 and player 1's payoff is plus 1. Now similarly, if both of them are showing different face of the coin, then player 1 will give 1 rupees to player 2. So here you can see, and here you can see this kind of game is called matching pennies. Now another game we have studied in the previous class, that is stag hunt game, and this as name suggests it captures the conflict or the situation or the strategic interaction when a group of hunter wants to hunt either a bigger animal stag that requires a larger coordination, so everybody in the group needs to pay attention. Another option is they can one individual can one individual can and not one individual can also choose by not paying that much attention to catching a stag and go for individually to catch a hare or hunt a hare. Then that individual will get the hare, but the individuals who are trying to catch the stag cannot, because the stag hunting require the everyone attention. So this kind of situation can be characterized by the stag hunt game, and this is the situation if both of them obviously both of in the group everybody prefer to catch a stag over the catch a hare. However, if anyone prefer to hare, then who prefers to stag will lose out, because that individuals who is preferring stag, that individual will not be succeeded to hunt a stag alone. However, the individual who defect with the other individuals and try to hunt a hare will be successful to do so and get a payoff one. So that is the case. So that situation can be represented by the stag hunt game. Now let me introduce uh, in this class another game which is called hawk tokens. Wait for a minute. So hawk top game. Let me introduce the octave game. Oh, it's not working properly. Let me do it again, then it will be okay. So, let me go to the page, then it will work properly. Okay. Let represent again, which is octave. Oh. So wait for a minute. So let me. So there is some glitch with my computer. So let me fix it. Then I will come back. I guess it is now okay. Now it is working properly. So octave game. Now here we are telling about a situation that is, as name suggests, hawk and dove. So here there are two strategies whose name is corresponding to hawk and dove. Now okay, let me hawk and dove. So suppose two animals are fighting over some prey. Animals fighting over some prey. Each can either be passive, so that is characterized by dove strategy, or be aggressive. Now each prefers to aggressive if other is passive, and passive if its opponent is aggressive. Okay, given its own stance, it prefers outcome which its opponent is passive. So given its own stance, so obviously among these two, so it prefers the outcome in which opponent is passive to which its opponent is aggressive. So let's see how can we. So one is passive strategy is dub. So what are the strategies are available? What are the action? What are the players? First players are two animal who are fighting. Two animals who are in a conflicting situation. So these are the players. What are the action available? Action is aggressive or passive. So that is aggressive is corresponding to hawk strategy, and passive that is corresponding to dove strategy. So hawk dove. What are the preferences? So every player's preferences are same. So if we write it from the player 1's perspective, then its most preferred outcome is that it is choosing a hawk strategy when opponent is choosing dove. Then when opponent is choosing dove and it opponent is choose dove, opponent choose. Now you can think about such situation like when two animals are fighting for getting a mate. So for mate choice they are fighting. If one individual is aggressive, then other individual become passive and leave the ground. Then the individuals who are aggressive will enjoy the mating and can successfully uh, take successfully um, successfully successfully get offsprings which bears its own gene. Now, in the other way, if the individuals who is not become aggressive, rather become passive and left the ground, that individual will be beneficial, because if both of them become very aggressive, then they may inflict serious injury to each other. That injury can induce death to any individual. So they prefer life life over serious injury. That's why the dove strategy is better for going to hawk situation. So this situation is more preferred. So obviously then the dove situation where everyone is left is preferred. Then the least prefer is that both of them is become very aggressive. Both of them become very aggressive. So dub situation means both of them are not getting something out of this conflict. Both of them are become passive and left the ground. But hawk strategy is that they are not successful. Successful. They are not successful in mating. However, they inflict each other due to the conflict. They induce into each other because of serious conflict. They may injure each other very seriously. So that is the less prefer. So now let me put numbers here. Suppose this situation is 3, this situation is this. Okay, let me, so since this is 2, this is 1, this is 0, and this is -1. Now game can be represented in this way. Now for player 1, hawk strategy, this is top strategy, this is again hawk strategy, this is top strategy. If both player do hawk of both of them get -1. If one individual dove another individual hawk, who the individuals who is going to dove strategy, it will get a pay of 1. However, the individuals who are playing hawk, that individuals will get, that means player 2 will get a strategy, get a pay of 2. And here as this is the individuals who are playing hawk will get 2, and the individuals who are playing dove will get 1. And here again dove strategy, that means they will get 0. Now this situation is hawk dove situation. However, this is not this means similar to the previous game. There is quite this applicability is not limited to the case of animal conflict. However, this situation can be modeled to the Cold War between two countries, because everyone wants to everyone wants to be shown as a very aggressive country. However, if both of them are showing aggressiveness to each other and started serious war, then both country be uh, will be will be in danger, because of will be in danger, and they may cause uh, serious situation in both of the countries if they both of them are start to behave aggressively and start a war between themselves. And then this situation is very worse like hawk strategy. And so they will most prefer that one country will showing aggressiveness and other country showing very passiveness. Then the one country is showing passiveness, then and another country is showing aggressiveness, then both countries shows each other passiveness. And third is the both country are showing aggressive behavior to each other. That way it may lead to a serious war. So that's it. Now let's introduce a concept of equilibrium, that is Nash equilibrium. Nash Nash equilibrium. So if anyone heard about the game theory, it is very obvious to know or listen about the concept of Nash equilibrium. Now Nash equilibrium is the situation that that dictate or that predict or that prescribe that what rational individual that we have studied in this class, uh, that what does this rational individual means. That means the rational individual means VNM rational individual. So I am talking about VNM rational individual who always wants to maximize maximizes maximizes the expected utility. Now, Nash equilibrium prescribe a situation that will show that if both of them clear are Nash in equilibrium, then no individual unilaterally wants to deviate from that equilibrium. In that sense, it is equilibrium. So, let me introduce what the concept is. So, let me start from the in general situation. Suppose there are two or more individuals who are VNM rational. They are playing or they are interacting strategically with each other. Now, in this situation, if you think about that, everyone wants to maximize her utility, or in means precisely, everyone wants their most preferred outcome. Now, since the preference can be represented by utility rather than saying that the individuals wants the most preferred outcome, we can equivalently say that the individuals wanting and individual's choice can be represented by the maximization utility, and it will be very helpful because in terms of mathematics we can this preference choice can be reformulated as a maximization problem. So from now onward we'll always say that one individual always wants a outcome which corresponds to the maximum utility, or I will say individuals which in the loose sense, which is not which is not in a stricter sense but in a loose sense, we can use the sentence that every VNM individual where the expected utility exists wants to maximizes her or his utility. However, if you think about the strategic situation, so suppose many players are in a strategic situation, and since every players are VNM rational, what they want always maximizes utility. Now, in a strategic situation, if everyone wants to maximize, however, the problem is in the strategic situation the outcome depends on every player. So depends on every player action. So as we have seen in our one of the lecture, in strictly competitive game, that logic still valid here. That is, we have seen that the action which is maximized, if the opponent choose one action, that action no longer remain the best action, or the action which is corresponding which yield maximum utility or payoff if the player changes his or her action. Suppose there are 3 actions of player 2 and 3 actions of player 1, then if player 1's action 2 yield her maximum outcome or maximum payoff if player 1 choose action 1. However, it is not in general true that same action, that is action 2 of player 1, will also yield him the maximum payoff when player 2 is choosing other action other than one. So that says that in general there is no way to maximize one player's action. So in general way to maximize one individual without information about other players action. So this is in general true. So what we have to search for, so that is called the Nash equilibrium. We have to search for, is there any action profile available. So action profile means that it is a set where every one action is described. Suppose action profile, what is action profile is, we have defined it previously. Now let me define it again. Profile, suppose n individual are present in a strategic situation, then our action profile means a set where it prescribes action for every individual. So suppose a1 for player 1, a2 for player 2, a3 for player 3, such that an for player n. So it's a collection of n actions, one actions for each player. So this action profile. So now we just change the question a little bit from the question that can one individual without the information about other players action, can one individual maximize her payoff or utility. So from that question, or we have seen that there is a problem in general, there is no way to maximize one individual's payoff without the knowing the other player's action. So that's why we just want to reformulate the question in a separate way. We are asking, is there a action profile who are in a strategic situation? That means suppose n player are in strategic situation, then is there a action profile, that means action for every individual, such that that action profile such that this action profile is in a sense maximizes everyone's utility given that other players utility. So by this statement I mean, so we are asking for, is there exist any action profile such that player, suppose player i's action ai, so that means player I in that situation getting a utility ai, given that the other players actions are a1 a2 a3 dot 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 n except ai. So other players action can be represented by ai, so ai minus a minus I. So this is suppose a, so this a minus I. So except I, if I take the I, suppose here a minus 1 will be the set a2 a3 dot 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 an. So that means if I take a1 from a, then it will become a minus 1. So that means the other player strategy, if I talking about the player 1 strategy, then other player strategy can be rewrite in short form by a minus 1. Here I am talking about the player 1 action is ai, and the all other players actions, other players action, all actions can be represented by a minus I. So in this situation the player I will get some payoff, and here I am talking about the pure action, so not talking about the mixed strategy that we have not introduced yet. So ai comma a minus 1 is maximum in sense that no other action other than ai, so that is ai prime will give him as much as payoff as he is getting from playing the action ai. So in that sense this ai is maximizing player i's utility, given that all other players stick to their action profile. So in a sense we are asking, is there any such profile exist where for here for all I, for every player. So this is true for every player, so that means for all I belongs to n. So that means we are asking, is there any action profile such that in a way everyone's utility is maximum, in a sense that if player playing action ai, then no, by shifting her choice from ai to ai prime, no, there will be no other ai prime or action such that it will give it will give the player I as much as payoff as the AI is he is yield by playing AI. So in that sense this is called the equilibrium, because in this situation, if you think about, if everyone plays the choice as prescribed by this action profile, then no player I wants to change her prescribed action. So this is equilibrium, because no one wants to unilaterally change her action, given that when every other individuals also stick to their action. So this action profile, this equilibrium or this action profile, if it existed, is called the Nash equilibrium. So this profile is called Nash equilibrium. Now the definition does not saying that for every game there should be a equilibrium corresponding here, since this is corresponding to players pure action. So this is not telling that for every game there exists a Nash equilibrium with pure actions, or it is not saying that that this is unique. So this is the definition of Nash equilibrium, but this equilibrium is not saying that there exists only does not says that existence, that for every game this type of Nash equilibrium exists for every game. And the second thing, this also not ensuring that it is not ensuring that for every game the Nash equilibrium is unique, that means only one Nash equilibrium is possible. We will see that there will be game where this kind of Nash equilibrium is not possible, and multiple Nash can be there in a game. So let me show you the Nash equilibrium of prisoner dilemma that we have studied in the previous class. So first Let us calculate the Nash equilibrium of prisoner's dilemma. Prisoners to so what is the game? So let me rewrite the game again here. So there are two strategies. One is remain quiet or think here also quiet or think. Now if both, we have seen that both of them quiet remain, that payoff will be represented by 2 2. If one thing 3 0, now 0 3, now 1 1. Here we will see that, or this strategy corresponding to everyone is adapting the strategy Fing Fing is the Nash equilibrium. This strategy is Nash equilibrium. Why this strategy is Nash equilibrium? We will see that if this action profile, it is obviously action profile because it associate a action with every player. So this is a action profile. Now we will see why this action profile is a Nash equilibrium. So we know that to be a Nash equilibrium, it has satisfied the property that is described by the above. That means every player has no incentive to deviate from the Fing Fing. That means the above strategy is saying that, above definition is saying that there will be no action AI such that by deviating from this action profile AI to AI prime such that it will gain gain us some amount of gain and in terms of utility. So that means let me again restate the statement. So there will be no other action other than the prescribed action profile by the Nash equilibrium such that individuals will adapt or shift from that action to other action AI prime such that the individual will be gained in terms of utility. Now here we will see that the Fing Fing will have the property. Now so here the player 1 has the two action, one is think or quiet. So first is, if player 1 wants to change from think to quiet, what amount of payoff it will get. So how, what, from think to where it can go, from think it can go from, so for player 1, for player 1 it can change from fin to quite. QUIT. Now the question is, if she changes her action from fin to quite, will she gain in terms of utility? Let's see what is the utility for player 1 of this fin. That is 1. And what is the utility of player 1 that correspond to when the player 1 shift from or deviate from the action quite fin to quite, adopt a different action that is quite, what you will get? If a player 1, what is the player 1's player 1's utility when she remain quiet and other things, that is corresponding to 0. So this is 0. So you see that there will be no incentive that player 1 will change from fin to quiet, given that when other he knows that the other player stick to remain to fin. Now the second property, so the property holds for the player 1. So we have to show that for every player there will be no incentive to change her action unilaterally, such that he can gain in terms of utility. Now for player 2, the same situation will be there. If fin will give him 1. Now the question is, will he choose from when player 1 does not changing her action, will the player 2 will change from fin to white? So what she will get if she change from fin to white? What amount he will get? Player 2 get in the, if when player 1 fin, when player 1 fin and player 2 remain quiet, what he will get? He will get the payoff corresponding to payoff is 0. So that means he cannot gain by deviating from fin to white. So for the both of the player, the the definition of the Nash equilibrium satisfied, that there is no other action such that unilaterally anyone can deviate from this prescribed action profile fin. So this is corresponding to the Nash equilibrium. However, anyone can say that the fin strategy is not the strategy which give them maximum outcome. Why they should choose fin when the remain quiet will give both of them a maximum payoff 2 2? So let's see that why this quiet is not a Nash equilibrium. Remain quiet is not a Nash equilibrium. So we have to check that whether the player has any incentive to change her strategy unilaterally from quiet. So what from player 1's first, you see from the player 1's perspective. So what the player 1 can do other than playing quiet, it is fin. So it is obviously the fin. Now let's see what is the utility of quiet. Quiet is 2. And what is the utility of fin when the player 2 remain? What it is? It is nothing but 3. So it is confessing that the player 1 confessing and become the witness before the court. So that's why it will get a maximum payoff that is corresponding to 3. So here you can see, obviously for player 1 there is enough incentive to change her strategy from white to become fin, or to be free riding over the over the individuals who remain quiet and get a get and get a means there is a option to maximize her payoff. So that's it. That is why player 1 always don't want to be, if she acts as a VNM rational player who wants to maximize her payoff, always tries to be become adopt a strategy correspond a strategy thing if from the quiet. So the quiet is not a Nash equilibrium because the player 1 has an incentive to deviate from quiet to think, because in this sense their the utility is increased. And for the player 2 also the same thing you will see for the player 2 also. Here I want to mention that if any individual has an incentive to shift from the strategy, if we can show that, then that action will no longer be a Nash equilibrium. So for the there, if we have shown that player 1 has enough motivation to shift her action from quiet to think, then it is enough that this is action is not Nash equilibrium. But for this for the generality we will show that the for the player 2 also from quiet to think will be a better option. For player 2 also remain quiet give her 2. However, if player 1 remain quiet and she think, it will yield her a pair of 3, which is obviously better than remain quiet. So that's why she always try to deviate from quiet. So that's why quiet is not a uh, not a Nash equilibrium. Similarly, one can see that the other options, that means quiet comma think is this is a Nash equilibrium. So you will find that for player 1, for player 2 this is not a Nash equilibrium, because obviously player 1s don't want to change her action. But if from the player 2's perspective, if you see player 2's payoff is this is equal to 0, but there is a better option to shift from okay no. So for it is from player 1's perspective. So if player 1 remains quiet and player 2 think, then there is a better option for player 1 also to become a think. So that's why it will give him, so quiet give him a pay of 0, and think will give him a pay of 1. So the always player 1 wants to deviate from this this outcome quiet thing. So this is quiet thing is not an Nash equilibrium, because player 1 has incentive to deviate from this strategy unilaterally. Second, for the strategy corresponding to here, another thing one should notice, that here the player 2 don't has any incentive to change her strategy from white think to white, because here it is getting pay of 3, here it is getting pay of 2. So there is no incentive to change her to think to quiet. However, for player 1 there is a incentive to change her strategy from quiet to think. So that is why the player 1 will always change her strategy from quiet to think. That's why it is a not Nash equilibrium. Now again the last option remain. It is similar to the one we described. So one is corresponding to, suppose player 1 is pink and other player 2 remain quiet. So here also you see that the utility of player 2 is such that the player 2 will always wants to change her strategy from pink from white to become pink, because that will yield her better payoff. So here it is getting payoff 0, but here it will get a payoff 1. So that strategy, since player 2 has an incentive from deviating from pink white to adopting a different strategy, so this is not remain no longer the Nash equilibrium. So now we have seen that this game has only one Nash equilibrium, and this Nash equilibrium very in a strict sense. So this is a strict Nash equilibrium. Here this game is also capturing from the outcome. This game actually capturing another property. Why this is called a dilemma? You can see that the two player always wants to choose the outcome corresponding to Fing because of the fear of free riding, that other individuals can free ride if she remains quiet. That means other individual can um, uh, can defecting or be free riding if he remains quiet. So that's why, although there exists a outcome corresponding to women's outcome, that is both of them remain quiet, will give them a maximum outcome, that is both of them will get 2 which is obviously better than both of them be Fing, but because of the fear of free riding they will choose, always want choose from Fing. So this is the dilemma, that they will face, that although there is a maximum payoff exists, we will choose corresponding to Fing out of the fear of free riding. So in many situations which will capture by the prisoner dilemma, though those situations will also be also can be can be analyzed by the same same Nash equilibrium. Suppose we have given now, as if you can recall, in the previous class we have given an example of two neighbor country are wants to build build a atom bomb or build a atom bomb. So if in that situation, if two neighboring countries wants to build atom bomb or refrain from making the bomb, is two available actions, and that situation can be can be recast in the form of prisoner dilemma, and we will find that the situation will be both country will build the bomb and both country will have the bomb. So that is corresponding to the Nash equilibrium, and obviously that is very bad situation. Obviously there is another available option will be there, that both of country doesn't have the bomb, over the both of country does bomb, but because of the free riding everyone tries to build the bomb by their own. So that is the situation. Now let us shift our attention to another game. Now next game, that is Battle of Sexes. So Battle of Sexes. Now let us go back here, and what was the payoff element? So payoff element was 21001. So our example of Battle of Sex game was that there are two players, male and female, male and female. And what are the options? They can go to a cricket match or go to a musical concert, cricket match or musical concert. The row player is the player male and the column player is female. And the payoff was as we have represented in the previous class. The payoff is 2 comma 1. Here this is 0 0, this is corresponding to 0 0, this is 1 2. Now see which are the Nash equilibrium. Basically see the cricket first. Now in the situation cricket, does anyone has any incentive to deviate from the situation? Let's see from the player 1's perspective. Player 1 what else can do? She can, or that male can, he can choose, he can choose musical concert. So from here to he can change. So the utility of player 1 of playing cricket is 2, and he can choose or he can deviate from cricket to music. And when the male stick to the option cricket, what the player 1 the male will get, that will get 0. So that means there is no incentive of player 1 from deviating the situation from cricket. And another situation is, let's see for the player 2 perspective. Player 2's perspective, u1 cricket will give her 1. However, if she choose other than cricket music and the player 1 stick to her action cricket, then the player 2, that means female, will get the payoff 0. That means if she deviate, it will lose her payoff. So that is, there is no incentive for both player 1 and player 2 from deviating immediately from the option the action profile cricket. So the cricket is a Nash equilibrium. Now let's see, is the option cricket comma music is a Nash equilibrium. So obviously what is the utility of the player 1? So the 0. And if that player, that male, changes her preference from cricket to music, what he will get in the music, the player 1 can get a payoff is 1. So that is 1. So that means by changing from cricket to music, in this situation when the female is stick to her choice music, the player 1 always can do better by choosing music. So that is, the player 1 has enough incentive to change from this action profile. That is cricket music is not corresponding to a Nash equilibrium. So this action profile is not a Nash equilibrium. And you can always see from the player 2's perspective also, cricket music is giving her 0. If she change to her option from music to cricket, she will get a pay of 1. So that means here also she can do better by changing her prescribed strategy. So that means that for the both player there is no incentive to stick with the prescribed action profile. So that means it is not a Nash equilibrium. Now another option is obviously the opposite one, and similarly one can see that music cricket give player 1 a pay of 0. However, by changing from music to cricket, player 1 can do better and will get 2. So there is always has a incentive of player 1 from changing the accent profile music cricket to cricket. That means when the player 2 is choosing cricket, the player 1 has incentive from change her accent music to cricket. So that means it is not a Nash equilibrium. And if you see from the player 2's perspective, the same thing is also from music what gave her pay of 0 of gave her music cricket gave her 0. However, if she changes when the other player stick to music, she changes her preference from cricket to music, she will get a pay of 2. So always player 2 also has incentive to changing unilaterally these actions. Is not a Nash equilibrium. Now the next question is whether the last option left, that music is Nash equilibrium and music. So let's see from the perspective of player 1, E1, music will give him a pay of 1. But if he wants to change his strategy from music to see a cricket match, he will get a pay of 0. So that means by changing from music to cricket, when the other player stick to music, the player 1 cannot do better. So that means there is no incentive to change from music for player 1 music to cricket music. So that means this is okay. So now we have to see also from the player 2's perspective. So if I see the player 2's perspective, player 2 in the music she yield a pay of 2. Now if she change her accent from music to cricket, she will get a pay of 0. So there is no incentive to changing, because by changing her accent from music to cricket, when the other players stick to music, there will be no gain. So that means there is no incentive for player 2 also changing from the accent music unilaterally. So that means from if the accent profile music in the accent profile music, there is no incentive for any individual to deviate from this situation unilaterally. So that means the music is a Nash equilibrium. So now if we can see that in the case of the battle of sexes games, there is two Nash equilibrium. one is corresponding to both players are going to a date to a cricket match, another is corresponding to both are going to a musical concert. Now we will see another game where there is no Nash equilibrium present, that is matching pennies. So there is no Nash equilibrium in a sense, so that up to now whatever we are talking about, it is called the pure Nash, because we are only talking about the Nash equilibrium in the sense of pure strategy. In that sense, the matching pennies game does not have any Nash equilibrium, but in the later class we will see that the matching pennies game has another kind of equilibrium which is called the mixed equilibrium. So let's uh, let's uh, leave that topic for the next class. So let us see that what is there an equilibrium corresponding to matching pennies. So what was the game? So let me see that. Okay, we know that what is the game. So one is corresponding to head, another strategy is tail, here also head, tail. Now we know that if both of them shows the same side of the coin, player 2 give player 1 1 rupees. So that means the player 1's payoff is 1 rupees and player 2 is minus 1 rupees, because player 2 is giving the player 1 a 1 rupee. And if so, here is the same situation, both of them showing head, that is same side of the coin, so this will be same as this. Now if both of them are showing different side of a coin, then player 1 will going to give player 2 a 1 rupees. So this will be player 1 is giving player 2 a 1 rupee, so player 2's payoff is 1 and player 1's payoff is minus 1. Similarly this situation also same. Now if you see that this situation, now in both of these two cases the utility of player 1 is same. So utility of head is 1 and also utility of tail. Now the question is, does player 1 wants to change from head to tail head? No, because in the tail head he will get minus 1. Similarly here from tail to change head tail, no. So that means in these two cases player 1 has no incentive to change from head to from this action profile. However, if you see the same situation from player 2's perspective, u2 head, in this situation it will get minus 1. Here also 2 head, it is getting minus 1. So now if you see and ask the question, does player 2 has any incentive from changing her strategy head to tail unilaterally? You will say yes, there is incentive, because in the, if she changes her strategy from head to tail here, he will get a payoff 1. So from headed to, if tail, it will get a payoff 1, so that means 1. And here from, sorry, this is corresponding to tail, and the same situation is tail. Now I asking the same question, is there any incentive for player 2 to change his strategy from tail to head? Writing it's wrong, so this is corresponding to head tail. So that is player 2 has an incentive to change from head to tail, given that player 1 is keeping her strategy to head. So why? Because there, by this way he can better off, or he can get a payoff, that is, he can better his payoff from getting -1 to +1. So you will always wants to change her strategy from this action profile to this. Now here from this action profile to player 2 has an incentive to change unilaterally from tail to head. Yes, you will see it will always have this incentive to change change his strategy from tail to where the player 1 is fixed. If player 1 is not changing his strategy from tail, player 2 has incentive to change her strategy from tail to head, because in this situation it will get a payoff 1 that is better than -1. So these two is not Nash equilibrium. And if you see another two situation is similar, that is corresponding to both of them showing different face of the coin. Now let's see that is there player 1 has an incentive to change from a tail, that is giving him -1, to tail. So player 2 does not changing the action, but is there any incentive for player 1 for changing his strategy from head to tail? Yes, because in this situation, tail situation, it will get a payoff 1. So that means this headed or tail is not Nash equilibrium. Here we will say that we are actually saying that there is incentive for player 1 to change his strategy from this action profile when the player 2 strategy remain fixed, that player 1 has incentive unilaterally from changing his strategy from head to tail, because it will give him a payoff 1, and which is better than -1. So this is not a so the strategy corresponding to head and tail, this is not a Nash equilibrium. Now the same situation is for tail head. In the tail head, player 1 has to give -1. Player has to give 1 rupees to player 1, so that means it gets a pay of -1. So will it change, or will it has, or does it has any incentive to change from unilaterally from tail to head when the other players is fixed her strategy to head? Yes, there is incentive, because in this strategy it will get a payoff +1. So that means here it is player 1. So player 1 has, in this situation, player was has incentive to change from this strategy head tail or tail head to unilaterally change from this action profile. So these two action profile is not also Nash equilibrium. So we see that no, in these two situation player 2 has incentive to unilaterally deviate, thus these two is not Nash equilibrium. And in these two situation, player 1 has incentive to change his action unilaterally. So that's why these two action is not also Nash equilibrium. No. So that means in this situation no pure Nash is exist. No pure Nash equilibrium. Now another thing we will want to see that, or in the next class, in this class I want to see another thing, that is what is the equilibrium of Nash equilibrium of the stag hunt game. Nash equilibrium of stag hunt game. So the Nash equilibrium of the stag hunt game is same as the battle of sexes. So let me rewrite the stag hunt game. Let me see what are the payoff. So 2, okay. So one is corresponding to stag, one is corresponding to here, other is stag, another is here, now this is 2, 2, this is 1, 1, this was 1, 0, this is 0, 1. Now if you see that here also the two Nash equilibrium is there, one is corresponding to stag. Here if you see this stag, in this situation the player 1 doesn't have incentive to change her action from stag to here stag, because in this situation it will get 1, but in the other situation it is getting 2. So that is, there is no incentive for player 1 to change unilaterally her strategy in this situation. And also for player 2, stag will give him 2 and stag here will give you 1. So there is no incentive to change her strategy from unilaterally from stag to here from this prescribed situation stag. So this stag is stag action profile is a Nash equilibrium. Now another thing is, if you see that this stag here situation is not a Nash equilibrium, because in this situation player 1 has always incentive to change from stag to here, because in this situation both will get a pair of 1, and for player 2 it is indifferent, stag and here it is also getting 1, and player 2 also in this situation has an incentive to change from stag here to stag, so that will give him a pair of 2. So both player has incentive to change from this action profile stag here, so that is why this is not a Nash equilibrium. Not Nash equilibrium. Let's see another thing, that u1 is here, stag is a Nash equilibrium because in this situation 0, but if player 1 has incentive from unilaterally change from here to stag, because it will give him pay of 2, so that means this is not a Nash equilibrium, not a Nash equilibrium. So let's see for the player 2's perspective, for the completeness, player 2 here stag give him 0, but if both of then changing to here, it will give him a pair 1. So obviously player 2 has also incentive to change from the here stack strategy, so this is not an Nash equilibrium. Now let's see the last option. Is the here is a Nash equilibrium? So from the player 1's perspective, it will give him a pay of 1, but if he chooses from here to stack, then he will get a pay of 0. So that means he he cannot do better by changing his strategy from here to stack in this situation. So that means here in the here there is no incentive for player 1 to change his action unilaterally. So let's see from the player 2's perspective. Here give him a pay of 1. Now if she change her strategy from his strategy from here to stack, it will get a pay of 0. So similar situation is appearing for player 2 also. By unilaterally changing his strategy, he cannot do better, he cannot get a better payoff. So that means player 2 has also no incentive to change his strategy unilaterally from here. So that means this strategy is a Nash equilibrium, since no player has any incentive to change her strategy unilaterally. So this is also a Nash equilibrium. So here we have seen that in this stag hunt game also, these two are Nash equilibrium. Both are going for stag and both are going for hunting a hare. However, wherever there is two Nash equilibrium, there is no guarantee which Nash equilibrium all the individual will adopt. So the theory of Nash equilibrium does not prescribe which equilibrium they should adopt. However, in this situation, which is just opposite to the situation of the battle of sex, where one equilibrium is preferred, most preferred by one associate. So there is two Nash equilibrium, so cricket and music, but in the first case this outcome is preferred by the male other than this, and this outcome is preferred by the female. So two parties prefer two different Nash equilibrium, so there is no guarantee which equilibrium they will choose. There is, in the theory, there is no way to distinct about the two Nash equilibrium. However, in the opposite to this battle of sex game, in this situation, the stag hunt game, the two equilibrium is different kind. The all individuals prefer the outcome stag over the here, because in the stag both of them will get a pay of 2, but in the here both of them will get a pay of 1. So both of those individuals prefer the outcome stag over the here. However, in this situation also there is no guarantee. There is, the theory cannot prescribe that the stag Nash equilibrium will be chosen by the player always over the here Nash equilibrium, because it's only prescribed which will be the situation where if the players remain there, they will be there forever. It's kind of Nash equilibrium is actually prescribing a steady state situation. So it only says that there exists, if there is some Nash equilibrium, it only says that if all individuals adapt that action profile corresponding to the Nash equilibrium, then the no individual has any incentive to unilaterally deviate from that action profile. That means it's corresponding to a steady state. So only the Nash equilibrium prescribe this. If there is multiple Nash equilibrium, in theory, in principle, there is no way to distinction between two Nash equilibrium, and the theory of Nash equilibrium does not suggest that individuals always choose one Nash equilibrium over another, and also does not guarantee that if we do experiment with real human beings, they will always adapt a Nash equilibrium. Nash equilibrium actually a normative theory. It only suggests that if if the player acts as a VNM rational, then what kind of strategy what kind of strategy will truly reflect the fact, and also take into account that is there any action profile. If all individuals remain there, they will be they don't want to change the action profile unilaterally. So that's it for today's class. In the next class we will learn about the mixed Nash equilibrium, and the what are the Nash equilibrium corresponding to the Hoctave game. So that's it for today's class. So thank you.